And to move from the abstract laws of motion to the physical reality of a machine like the Raptor 3, one must shift their perspective from physics to high-stakes plumbing. While the previous section established that a rocket is a momentum machine, the physical manifestation of that machine is a complex arrangement of hardware designed to manage extreme pressures, cryogenic temperatures, and corrosive environments. And to visualize the anatomy of a rocket engine without getting lost in a labyrinth of pipes and valves, it is helpful to look at a common, albeit much smaller, terrestrial device, the industrial high-pressure power washer. And at a construction site or a shipyard, a heavy-duty power washer performs a specific task. It takes a low-pressure fluid, specifically water, subjects it to immense mechanical work via a pump, and then forces it through a specialized nozzle to create a high-velocity stream capable of stripping paint or cutting through grime. The Raptor 3 is, in essence, the most powerful pressure washer ever conceived. However, instead of cleaning a driveway, it is designed to wash a 5,000-ton stack of stainless steel into orbit. And to understand the anatomy of the Raptor 3, we must examine its three primary systems: the reservoir, which includes the tanks, the motor, which includes the turbopumps, and the spray head, which includes the nozzle. In the reservoir, managing the cryogenic torrent, every engine begins with its source of potential energy. In our power washer analogy, this is the water tank or the garden hose connection. For the Raptor 3, the reservoir consists of the massive propellant tanks of the Starship and the super heavy booster. And unlike a garden hose, which provides a steady, low-pressure flow of room-temperature water, the Raptor's reservoir stores subcooled liquid methane, LCH4, and liquid oxygen, LOX. These are not merely fluids. They are high-density energy carriers kept at temperatures hundreds of degrees below zero. At these temperatures, materials behave strangely. Common rubber seals shatter like glass, and standard lubricants freeze into abrasive solids. And the anatomy of the engine begins at the interface between these tanks and the engine's inlet. In the Raptor 3, these inlets are designed to handle a flow rate that is difficult to visualize. Imagine a standard backyard swimming pool containing about 20,000 gallons of water. If you were to hook a single Raptor 3 engine to that pool, it would suck the entire volume dry in less than 30 seconds. And this flow must be laminar and consistent. Any bubble of gas, cavitation, or unevenness in the flow entering the engine could lead to pogo oscillations, rhythmic surges in pressure that can vibrate a rocket to pieces. Therefore, the plumbing of the engine starts with massive, insulated feed lines that ensure the propellants remain in a liquid state until the very millisecond they are needed. In the heart of the machine, the turbopumps. If the tanks are the reservoir, the turbopumps are the high-performance motor that drives the entire system. In a domestic pressure washer, an electric motor or a small gasoline engine turns a pump to increase water pressure. In the Raptor 3, the motor is a pair of the most power-dense machines on the planet. And each Raptor 3 engine contains two primary turbopump assemblies, one for the liquid oxygen and one for the liquid methane. To appreciate the scale of work being done here, consider that the turbopumps on a single Raptor engine generate more horsepower than several dozen Formula One cars combined. Their sole job is to take the lazy fluid coming from the tanks and compress it to pressures exceeding 350 bar or 5,000 plus psi. And the anatomy of these pumps is a masterclass in metallurgy. At the center is the impeller, a spinning disc with curved blades that flings the propellant outward at incredible speeds, converting rotational energy into fluid pressure. Because the Raptor 3 uses a full-flow staged combustion, or FFSC cycle, these impellers are driven by turbines that are themselves spun by high-temperature, high-pressure gas. And this creates a brutal environment. On one side of a thin metal seal, you have liquid oxygen at negative 180 degrees Celsius. On the other side, just centimeters away, you have a turbine spinning at tens of thousands of RPMs, bathed in hot, oxygen-rich gas. If those two fluids ever meet unexpectedly, the result is not a mechanical failure. It is a localized explosion that turns the engine into a shower of molten green copper and shattered superalloys. And the Raptor 3 pumps are unique because SpaceX has moved away from the bolt-on philosophy of previous iterations. In earlier versions, specifically Raptor 1 and 2, the pumps were surrounded by a chaotic web of external sensors, bypass lines, and purge valves. In the Raptor 3, much of this circulatory system has been integrated directly into the housings. This reduces the number of potential leak points, a critical factor when you are dealing with fluids that want to expand 800 times in volume the moment they escape their containers. In the sculptor of force, the nozzle and the bell, once the turbopumps have pressurized the propellants, and they have been mixed and ignited, a process we will explore in the next section, the resulting gas is a chaotic, high-energy plasma. Left to its own devices, this gas would expand in every direction, creating a massive explosion but very little directed thrust. And this is where the third part of our anatomy comes in, the nozzle, often referred to as the bell. In our pressure washer analogy, the nozzle is the adjustable tip at the end of the wand. By narrowing the opening and then flaring it out, the nozzle dictates the velocity and shape of the stream. And in a rocket engine, the nozzle performs a specific thermodynamic trick. It consists of two parts, the throat and the skirt. The throat is the narrowest point of the engine. As the high-pressure gas from the combustion chamber tries to squeeze through this tiny opening, it is forced to accelerate to the speed of sound, Mach 1. And once the gas passes the throat, it enters the bell. Because the bell widens out, the gas is allowed to expand. As it expands, its temperature and pressure drop, but its velocity skyrockets. This is the Joule-Thomson effect in action, coupled with supersonic flow dynamics. The nozzle shape is mathematically optimized to ensure that by the time the gas leaves the rim of the bell, its internal pressure is as close as possible to the surrounding atmospheric pressure. And the Raptor 3 bell is not just a hollow cone of metal. It is a sophisticated heat exchanger. The temperatures inside the exhaust stream are hot enough to melt any known metal instantly. To survive this, the skin of the nozzle is actually a honeycomb of thousands of tiny channels. Before the liquid methane is sent to the combustion chamber to be burned, it is first pumped through these channels in the nozzle walls. This regenerative cooling allows the freezing cold fuel to soak up the heat of the exhaust, protecting the metal and preheating the fuel for better combustion. It is a closed-loop system where the engine's blood, the fuel, keeps its skin, the nozzle, from vaporizing. And the mental blueprint, integration and simplification. When you look at a photograph of the Raptor 3, the first thing that strikes you, especially if you are familiar with the Space Shuttle's RS-25 or even the Raptor 1, is how clean it looks. It lacks the spaghetti of wires, tubes, and external components that typically define aerospace hardware. And this is a deliberate anatomical choice. SpaceX has moved toward a monolithic design. By using advanced 3D printing or additive manufacturing and complex casting, they have moved the engine's nervous system, the sensors and data lines, and its arteries, the propellant manifolds, inside the primary structures. And this internal integration serves several purposes. Mass reduction. Every bolt, flange, and bracket adds weight. By printing the cooling channels and sensor ports directly into the pump housings and chamber walls, SpaceX sheds hundreds of kilograms. Aerothermal shielding. During the violent re-entry of the Starship or the Super Heavy booster, the engines are exposed to extreme heat and plasma. External lines are vulnerable. By tucking the anatomy inside a smooth exterior, the engine becomes its own heat shield. Rapid reusability. In a traditional engine, a technician might have to check 1,000 individual joints for leaks after every flight. In the Raptor 3, the number of external joints has been reduced by an order of magnitude. And this blueprint of the engine, tanks feeding pumps, pumps feeding the chamber, and the nozzle shaping the result, is the physical framework upon which the entire Starship program is built. However, having a reservoir, a pump, and a nozzle is not enough. To create thrust, you need to initiate the most controlled, violent, and sustained chemical reaction in the history of engineering. And the hardware we have described is merely a cage. It is a vessel designed to contain a storm. The pumps provide the pressure, and the nozzle provides the direction. But the soul of the engine lies in the moment those two cryogenic fluids meet and decide to stop being liquids. And to understand how SpaceX manages this transition without the engine turning into a literal bomb, we must move from the anatomy of the machine to the chemistry of the flame. We must look at how the Raptor 3 manages the delicate balance of controlled destruction that occurs millions of times per second inside its heart. And as we have seen, the physical layout of the Raptor 3 is a triumph of simplification, turning a complex web of machinery into a streamlined, integrated power plant. But even the strongest metal cage can be melted if the fire inside is not perfectly managed. This leads us to the most critical phase of the engine's operation, the transition from fluid flow to fire. And 1.3 combustion 101, how to safely explode your way to orbit.